Welcome to Lecture 11 for Geography 136. In this lecture, I'm going to be talking about the basics of remote sensing, as well as one of these analysis processes that you can conduct just using remote sensing data, which is called classification or image classification. So this is going to be a pretty brief introduction to both of these things. I'm actually teaching the remote sensing class in the fall, and we'll go in much more depth into both of these, spending at least one full lecture on each of these basic topics. But for now, we're going to do just a quick overview of these most important parts of remote sensing and classification that are useful for analysis. So just an overview of the parts of this lecture. The first half or so is going to be focused on looking at the basics of remote sensing. This part should all be a review from an introductory GIS class. There might be a few new things to learn from this, but it's also just good to review this kind of stuff. So I'm going to focus on what remote sensing is, what the basics are, how we get images of Earth's surface, and what it means to conduct multispectral remote sensing. Then in the second part, I'm going to talk about classification methods. There are a few different ways that we can say what something on the ground is using GIS software. So classification means taking an image of what we see on the ground and actually clumping together those pixels or areas on the ground into specific groups based on something like land cover. Usually we're looking at land cover in remote sensing. But with object-based classification, as I'll mention, you can also classify specific objects like a tree or a car or a house. You can go beyond just saying like what general type of feature exists on the ground. So the thing that makes remote sensing possible is the electromagnetic spectrum. This is the entire range of energy that moves at the speed of light and is ultimately emitted by the sun. So we get electromagnetic energy coming into Earth's atmosphere, lighting up everything. That's like the energy that we get that enables us to see. But the visible spectrum of electromagnetic energy is only a small segment of this entire electromagnetic spectrum. So it's from about 400 nanometers to 700 nanometers. That's seen here. It's kind of blown up in the bottom right here. But of course, we have a wider range of electromagnetic energy than just this visible spectrum. On one end, we have radio waves, which are like really long wavelength, not as powerful or high energy waves. On the other end, we have X-rays and gamma rays, which are much higher energy, shorter wavelength. These two extremes aren't usually that important for remote sensing, but the areas just on either side of the visible spectrum are really important for remote sensing too, because those are things that we're able to sense with the sensors we have. So besides the visible spectrum, with remote sensing, we're really interested in the infrared part of the spectrum too. So this electromagnetic energy travels all around the universe from different sources, but the energy that ultimately makes it from us originates from the sun. So the energy comes from like this general direction of where these red lines are coming from the sun, makes it into Earth's atmosphere. This energy runs into just all the objects on Earth's surface, our bodies, a bench, a tree, everything. Multiple things can happen as this energy is making it through our atmosphere or when it runs into some type of matter, whether it's gas, liquid, solid. This energy reacts with all these different things in different ways based on the property of that substance. So multiple things can happen once that solar energy, that electromagnetic energy, makes it into Earth's atmosphere. We have different names for these different things that can happen. Transmission means that energy passes through the substance or passes through that type of matter. The atmosphere, for instance, transmits a lot of solar energy because that energy ultimately makes it to Earth's surface. A window is also really good at transmitting visible light. Light just travels straight through a window. Something that doesn't transmit well is like an opaque wall that obviously doesn't transmit the energy. It doesn't pass through a wall. But if energy isn't transmitted, other things can happen. So the energy can be absorbed, and that means that energy is integrated and made a part of that object. So many objects absorb some of that electromagnetic energy. That is when those objects are getting heated up by solar energy. That's absorption. It actually excites the molecules of that substance. Energy can also be reflected. That's when that energy is returned in the same predominant direction that it came in at, but at a slightly different angle. So a mirror reflects visible light. If you shine a laser at a mirror or shine a flashlight at a mirror, that light will bounce off. It's not being absorbed by the mirror. It's not passing through the mirror and being transmitted. Energy can also be scattered. This is where the energy hits that substance, hits that matter, and then the direction of that incoming energy is kind of just randomly changed and the energy heads off in all directions. We also have emission or re-radiation of energy. Something can actually absorb energy, such as from the sun, and then that thing makes that energy as part of its own matter, and then re-radiates it back out, just like the sun, but it does so usually at a lower energy wavelength, a longer wavelength. So the Earth actually re-radiates energy back out to the atmosphere, and that's how we get most of the heat at the lower level of Earth, is because of this emission of radiation. The sun emits really high energy radiation. It hits Earth's surface. Earth's surface is able to absorb that energy, make it a part of those objects at the surface, and then those heated objects actually re-radiate that energy. For remote sensing, we're mostly focused on looking at reflectance, looking at the wavelengths that come back to the atmosphere or come back to space. Again, those visible wavelengths, infrared wavelengths, they can bounce off a thing, reflect off a thing, and they get sent back the same direction that they came from. That's what we're seeing when we see objects in a certain color, and we're looking at the world in this visible part of the spectrum. Sometimes in remote sensing, I'm not going to talk about it too much in this lecture, it's a little beyond the scope of this lecture, but we also measure emission, so you can actually measure the heat that's radiated out from Earth using remote sensing as well. This is not measuring reflectance from Earth, because it's not actually bouncing that energy from the sun back out. It's emitting its own energy back out after it has absorbed energy from the sun. But again, that's outside the scope of this present lecture. So remote sensing is carried out with something called sensors. Sensors are equivalent to cameras on board remote sensing systems. A sensor can be on a satellite, a sensor can be on an airplane. A sensor basically measures radiation at a specific range of the spectrum. A sensor might measure the amount of green reflected, the amount of blue reflected, the amount of infrared. So a sensor really is analogous to a camera, but it's a camera that a lot of times is limited to taking a picture in a certain wavelength range along that electromagnetic spectrum. So each range of wavelengths that's detected with one of these sensors is called a band. So an individual sensor may have the ability to take these images in different bands. So take a red image, a green image, a blue image. And these will all be separate images where we're basically just measuring how much reflectance there is, how much the objects that we're taking a picture of are reflecting energy in that part of the spectrum. So the sensor converts that incoming reflectance that it's measuring into a digital number. So that's seen on the right over here. We're looking at a remote sensing image with one band specifically. If you're just looking at one band, we're only measuring brightness in that part of the spectrum, so it's going to be a black and white image. If you zoom in, once you get really close, like all rasters, which all remote sensing data ends up as a raster, you get a grid of pixels that corresponds to how much light is being reflected in that part of the spectrum. So a white pixel has a lot of reflectance of light. A darker pixel isn't reflecting that much light in that part of the spectrum. The resulting raster has a range of radiance values. That's the brightness within that range of wavelengths within the electromagnetic spectrum. So usually these are coded to range between 0 to 255. 0 is black, which basically means there's no reflectance. All there is absorption in that part of the spectrum. White is the highest radiance. That means there's a lot of reflectance in that part of the spectrum. And so the number that corresponds to this reflectance in each band is called the digital number. It's a converted radiance value that takes in that amount of actual reflected light and puts it into this code of 0 to 255. This slide illustrates the bands that existed on the two last Landsat satellites, the two last Landsat sensors that have been sent up into the atmosphere to continuously image our Earth. At the top right, we have the bands that correspond to Landsat 8. There's 11 different bands here that all measure the reflectance or radiation in different parts of the spectrum. So band 1, for instance, it says coastal aerosol right there. That corresponds to a very specific range from 0.43 to 0.45 micrometers. Red is another location in the electromagnetic spectrum. Red consists of wavelengths from 0.64 to 0.67 micrometers. So these 11 bands correspond to areas where there's high reflectance on Earth's surface, because we want to measure those parts of the spectrum where there's a lot of reflectance, so we can draw differences between different objects. So the graph on the bottom left shows the entire relevant part of the electromagnetic spectrum. This is most of the energy that makes it to Earth's surface and is reflected or radiated back away from that surface. Those gray peaks and valleys in the back illustrate how much energy at those specific wavelengths make it through the atmosphere and end up hitting Earth's surface as making it to Earth's surface, ultimately being reflected away by Earth's surface. So if we go down to the far left, that's kind of in that visible part of the spectrum, 400 to 800 micrometers or so. There's a decent amount of atmospheric transmission there, and it's that important visible part of the spectrum. So a lot of those bands are shown as being located in that part of the spectrum. So where we see like the band 1, 2, 3, 4, those correspond to those wavelengths in the top right in that table. That's that range with which they're imaging. As we move further to the right on this graph, we have longer wavelengths. That means lower energy radiation. In this case, these are the infrared areas, infrared parts of the spectrum. Infrared light we can't see, but it does make it to Earth's surface and it's reflected away by some objects. Plants, for instance, are really good reflectors of infrared light. Just like plants reflect green in the visible part of the spectrum, they also reflect a lot of this infrared light. We just can't see it. So it's really important to measure infrared, and we have a couple different areas that we measure infrared energy in. So the near infrared, that band 5 on Landsat 8, that's this reflectance that plants have. As you get to these further out, even longer wavelengths, these are actually parts of the infrared part of the spectrum where heat is being radiated back out. It's not actually anymore kind of just like analogous to visible light. It's actually these longer wave infrared wavelengths that are actually heat or thermal energy. This is also a little bit outside the scope of this lecture, so we're not going to talk too much about thermal imaging, but you can get measures on heat from Landsat satellites. We're going to focus more on the visible part of the spectrum and the near infrared, because these are more important in classifying the things we actually see and want to learn more about on Earth's surface. Another band worth mentioning is this band 8. This is called the panchromatic band. It senses a wider range of electromagnetic energy being reflected back from Earth's surface, and because it reflects over this wider range, you can actually get higher resolution data pretty easily, even from this Landsat satellite. You end up with 15-meter resolution for this data, but because it's over such a wide range, it can't distinguish colors. It's just detecting all of the energy that makes it back to the satellite overall, rather than being able to detect like what is green, blue, red, infrared, etc. It just says this is the amount of light coming back. Because there's so much light coming back, we can have a finer scale image, but you can't distinguish different colors with this band. So the sensors, like we saw on the last page, are what are called multispectral sensors. Landsat is a multispectral sensor. And what that means is, as mentioned on the last slide, these sensors can detect radiance or reflectance across specific wavelength ranges in the spectrum. They usually have more than one, maybe between 3 and 15 bands, or 3 to 15 areas within the spectrum where they can detect this reflected energy. With Landsat 7, so one Landsat ago, we're currently on Landsat 8, as we saw on the last slide. There's 8 of these bands, so it's a multispectral sensor with red, green, blue, near infrared, 2 different shortwave infrared parts of the spectrum, thermal infrared, and that black and white panchromatic band. With multispectral imaging, there are going to be gaps between the ranges. We don't have continuous zones, so some parts of the electromagnetic spectrum aren't actually sensed. There are also hyperspectral sensors, so they kind of fix this problem of having gaps between different bands. With a hyperspectral sensor, there's hundreds of continuous zones. The reflectance of an individual pixel is sensed in all possible colors along a continuous range of different wavelengths. However, this isn't really a feasible technology to use at these larger extents. If we're looking at actual landscapes, we don't usually use hyperspectral sensing. It's just not feasible. Most of these hyperspectral sensors are kind of in the realm of experimentation. They're not super useful on a day-to-day basis. They're overkill for most Earth observation requirements and would just be hard to work with. All right, so again, each of these parts of the spectrum sensed by a multispectral sensor is referred to as a band. A sensor like Landsat has 8 to 12 bands, depending on which Landsat you're looking at. Each band on that sensor, again, just measures the intensity or brightness of what's sensed in that specific part of the spectrum. So the band displayed by itself will be a grayscale image. You'll just see a black and white image. There won't be any color. So even if band 3 is red, if you just look at band 3 alone, it's going to be black and white because it shows how much reflectance there is in the red part of the spectrum. So things that we see as red will show up as very bright in band 3, whereas things that don't really have any element of red within them are going to show up as really dark within band 3. Likewise, band 4, if we're looking at Landsat 7, is going to be that near infrared part of the spectrum. We can't actually see this, but you're going to get brightness in band 4 just corresponding to how much reflectance in that part of the spectrum there is. And plants reflect a lot of this near infrared energy. So with band 4, plants are going to show up as really bright. However, in software like ArcGIS or ENVI or ERDAS Imagine or Adrizi, there's all sorts of different software that can deal with remote sensing data. You can combine 3 bands at a time to create a color composite. So you basically use the primary colors of red, green, and blue to visualize each band. And when you combine these bands in this way, they appear as this colored combination between them, a combination of red, green, and blue, which is visible to us. So if you take those bands that are measuring the red, green, and blue parts of the spectrum and put them in their corresponding RGB slots, then you'll get a true color image. It'll just look like a photograph because the red, green, and blue are going to combine as they actually do in the real world. You get those different components of those real world items, just as you would in like a normal photograph. But you can also portray the brightness of another band, including those bands we can't see naturally, like the near infrared, as one of these primary colors. So the image at right has infrared displayed as red. So that image shows up red. That's actually like a forested area. That's Mount St. Helens in Washington State. Because there's so much vegetation in this area and vegetation really reflects the infrared part of the spectrum, the image appears mostly red because we made near infrared look like red. There's so much reflectance in the near infrared that the image shows up as red. So this is called a false color composite. We have a true color composite. That's when you put the blue band into that blue slot in the remote sensing software, the green band into the green slot, red band into the red spot. You get a true color composite. But if you mix those up, change them around like the image to the right over here, then that's called a false color composite. You're still compositing, you're combining 3 different bands together, but you're not looking at them in the same way that they actually exist according to our eyes. So here's a comparison of that image from the last slide, visualized as a true color composite and as a false color composite. There are different false color composites that exist. This again is that false color composite where we have the near infrared visualized as red. This is a pretty common visualization technique to draw out differences between photosynthetic vegetation. So different color composites exist that focus on drawing out differences among different types of objects. So usually when you see a red image like that, that's when we have that near infrared plopped into the red band. With Landsat 8, that would be a band 5, 4, 3 composite. Or in Landsat 7, it would be a 4, 3, 2 composite. But if you combine bands in different ways, you can draw out subtle differences between phenomenon that actually look pretty close when looking at a Landsat image with more sensitivity than when you're looking at it just with like its natural color. So there are some well-known and often used band combinations that you would use for investigating specific phenomenon. So let's look at a couple using Landsat 7. The band numbers actually change with Landsat 8. So these are a little bit different when you're looking at Landsat 8. But just for this example, we're going to look at Landsat 7. Again, all those bands are described on the top right up here. There's 8 different bands. Blue, green, red are 1, 2, and 3. So in remote sensing software, there's 3 slots that correspond to red, green, and blue visualizations based on those brightness values. If you plop the band 3 into red, band 2 into green, band 1 into blue, then you have a true color composite. So this is a 3, 2, 1 image where you'll end up with like basically a photograph of your area that you'd expect. That red looking image on the last slide, that was a 4, 3, 2 composite. That's where we put the near infrared in red, the red in green, and the green in blue. So you end up with those bright red values in the near infrared part of the spectrum. 742 is another common band combination. That's what's shown on right here around London. This has infrared bands shown as green. So you end up with that 4, that near infrared in the green slot in the visualization software. That makes the vegetation really appear as bright green, but you're actually not visualizing green, you're visualizing near infrared as green. With 742, if you look at band 7, you're also using shortwave infrared, which is slightly longer wavelength than the near infrared, further away from the visual part of the spectrum. 453 is good for looking at moisture differences in soil. There are other combinations that are good for looking at like urban areas or coastlines. It's fairly easy to find lists of these like useful different color composites online. Now, once again, it's important to note that these aren't universal values. If you're using a different multispectral sensor, including even Landsat 8, it's going to be different numbering for each of these common composites. So true color will be 432 instead. So keep that in mind when you're doing the lab, because for this lab, we're using Landsat 8 data. So we just talked about combining bands to visualize these remote sensing images in different ways. There's another way to combine bands that's really useful, and it kind of fits within the looking at analysis techniques for remote sensing and looking at visualization techniques, because it's really just another way of combining bands, but it lets you get more information about what's actually going on the ground. So we have what are called indices that are created from multiple bands. You can use a ratio of 2 bands to draw out subtle differences. So for instance, if soil has a high reflectance in one band and a low reflectance in another band, a ratio of that high reflectance band to that low reflectance band will make soil even brighter compared to other things. So if you're looking at one specific thing, you can accentuate the differences within that thing by creating a band ratio. So you might create a ratio of near infrared to red. That's actually one we'll look at. That's used in this NDVI calculation, but you can create a ratio of any band to any other band. So band 3 to band 2, band 2 to band 1. Then you end up with a numerical value for the output. Instead of just a reflectance value, you get a ratio of these 2 different bands. NDVI, or the Normalized Difference Vegetation Index, is probably the most commonly used index. It's a little more complicated than a simple 2-band ratio, but it works in a similar way. We're just modifying the visualization or the value in a cell based on the relationship between 2 different bands instead of just looking at one band on its own. NDVI really accentuates areas of highly photosynthetic vegetation, that really, really green, really bright in the near infrared vegetation from other areas. So by using these 2 bands, the near infrared and the red together, we look at the difference between the near infrared and the red. So a big difference will have a large value on the top of this ratio. A small difference will have a small value in this ratio. And then we divide that by near infrared plus red. So I'll show an example on the next slide, which will illustrate this with actual numbers and help make a little more sense of this. But what you end up with are numbers that range from -1 to 1 instead of whatever that digital number or brightness value was previously for each of those pixels with each of those bands. So in the picture in the top right, on the left side, we have a false color composite. Those areas of red have really bright photosynthetic vegetation. Those correspond to areas of high NDVI. So you get a high positive value for where NDVI is really high. That means that there's a lot of near infrared and not very much red in each of those pixels. Meanwhile, those reddish areas, when visualizing the NDVI, are closer to a -1 value. And if you look at the image they started from, that looks like it's just a glacier or snow or something like that. There's no vegetation in those areas at all. So if you plug a really low value for near infrared for each of those pixels into the NDVI calculation, that first part of the equation, the NIR, that's going to be pretty much 0, which will give you a lower NDVI overall. So this is a useful visualization of the construction of the NDVI index. With a green, bright green photosynthetic tree that's also going to be really bright in the near infrared part of the spectrum. If you look at that near infrared light coming in, bouncing off, about 50% reflected. That's really high. That tree on the right, it's actually still pretty high in the near infrared part of the spectrum, so about 40% reflects off. The corresponding part of the visible spectrum, the reflectance is a lot lower on that tree at the left. Those are dark leaves, so they're not going to reflect as much. The part of the visible spectrum on the right has a lot higher reflectance at about 30%. If you just plug in these values, these percentages as proportions into the equation, with the green tree, that really bright green, you get a high value for near infrared with 0.5, a really low value in the visible part of the spectrum. Because it's relatively dark, it's absorbing a lot of that visible light. And then you normalize that, so you put them added together under the bottom. Because that top part is such a large value, you end up with a high value of NDVI. So 0.5 minus 0.08 is still a big number. When you divide that through, you get 0.72. On the right, because that visible light is reflected really well by that deader tree that doesn't have those green leaves, you end up with a small numerator, 0.4 minus 0.3, divided by the combined value of those two, and you end up with a smaller value for NDVI overall. So you don't have to know how to calculate NDVI by hand or anything like that, but it is important to understand just what's happening when you look at an index or when you're comparing different bands together. And the fact that something like NDVI or other indices that exist are basically just drawn from the combination of different bands together. It's not any sort of crazy, really complicated equation. It's just what you see right here. In addition to NDVI, there are other indices that are commonly used. NDWI is the Normalized Difference Water Index. This is pretty good for looking at differences in water and soil moisture content. Then another one is MSAVI. This is the Modified Soil Adjusted Vegetation Index. This deals with soil brightness, and you can really look at the differences in different types of soil pretty effectively. So each of these is calculated in a similar way to that NDVI calculation. This slide really illustrates why you would want to do an NDVI calculation. So it shows NDVI at the bottom right compared with other band combinations. So at the top left is a true color image. If we were in an airplane looking down, that's what these fields would look like to us. The false color image, visualizing that infrared part of the spectrum, causes vegetation to appear red. The really photosynthetic vegetation reflects a lot in that near infrared part of the spectrum, and the areas that we see as green show up as bright red. They really jump out for the visualization, and it's clear to see where the living, verdant, bright vegetation is. But NDVI gives us something different. It gives us much better separation of the highly photosynthetic vegetation from just the surrounding fields that have really limited vegetation. So the high values are shown as a really bright green. The red and orange areas are really low NDVIs surrounding those bright green fields.